Okay, the function d1, which we proved that it is a metric on R2, the function d1, which we have seen is a metric on X, where X is R2, can also be shown to be a metric on X when X is Rn, where n noun is bigger than or equal to 3 bigger than 2 actually. Because for n equal 2, we have dealt with that. So we can also show that d1 is a metric on Rn. That means when n is 3, we have R3, R4, R5, and so on and so forth. On all those spaces, those finite dimensional spaces, the function d1, if we define it in the way we defined it before, also remains a metric. So what do I mean precisely? What I mean is that if x is equal to Rn, and then we define d1 on x cross x into R by d1 of x comma y equals summation I from 1 to n, absolute value of xi minus yi. Then d1 is also a metric on Rn. The verification is exactly the same argument as the one we did for the case n equal 2. So I leave it for you to check on your own that this function so defined is a metric on Rn. Yet another example. You see, like I said before, the more examples we take, the more knowledge we have about how to verify that a given function is a metric. Yeah, this is as a result of the experience I have. Some students, when you just give 1 or 2 examples, they will stick in their mind memory that this is the only way all functions that are called metrics come. And so if you shift a little bit from the ones you gave them before, they do not seem to understand what is going on. So we need to supply as many examples as possible so that as the students go through the videos, they get used to showing how knowing how to show that a given function is a metric. All right. So let us take x to be Rn, and then we define d infinity on x cross x into R by, for any element of this set, when this function d infinity acts on x comma y, we give the result to be maximum between absolute value of xi minus yi, 1 less than or equal to I less than or equal to n. So if we define this function like this, then d infinity is a metric on x. We're going to verify that this is a metric, but I'm only going to deal with the first one and the last one because the symmetric condition is not a problem, so anybody can attack that and come out with it. To verify A1, let's take x and y, capital X, again arbitrary. It is not difficult to see that the function is well defined, so that is not an issue to dwell on. So we take x and y here. X, look, if x is in capital X, it means that x is of the form x1, x2, up to xn. So it's n tuples. of real numbers with x1 in R, x2 in R, up to xn is also a real number. So that's what we mean by saying x is here. Similarly, if y is here, you know how to represent it too. It means y lies here means I can write y as y1, y2, up to yn, with y1 in R, up to yn also in R. So that's what we mean. Similar to what we did in the case of D1, we know that absolute value of xi minus yi is bigger than or equal to 0 for all I, 1, 2, up to n. If this is true, then the maximum of all of them will also be bigger than or equal to 0. So, maximum absolute value of xi minus yi, 1 less than or equal to I less than or equal to n, is also bigger than or equal to 0. What we have is that the infinity of x comma y is bigger than or equal to 0. Next, we want to verify that if the infinity of x comma y is 0 if and only if x is equal to y. So how do we do this? Notice that the infinity of x comma y is nothing but the maximum between absolute value of xi minus yi, 1 less than or equal to I less than or equal to n. So, if this maximum is equal to 0, we know that every element of the set we're taking the maximum is less than or equal to the maximum. So what do I mean by that? What I mean is that absolute value of xi minus yi is less than or equal to the maximum. Absolute value xi minus yi, 1 less than or equal to I less than or equal to n. This is true, but our assumption is that this maximum is 0. So we have this is 0. If this is 0 and this is less than or equal to this, so we get that absolute value xi minus yi is less than or equal to 0. I equal 1, 2, up to n. If this is less than or equal to 0, but we know that absolute value of any real number is bigger than or equal to 0. So what we have is that 0 is less than or equal to absolute value of xi minus yi, and this one is less than or equal to 0 for all I equal 1, 2, up to n. Good. With these two inequalities, we get immediately that absolute value of xi minus yi is equal to 0. I equal 1, 2, up to n. And so this means that xi is equal to yi. For each I equal 1, 2, up to n. So from what we have here, we know that the infinity of x comma y is 0 if and only if x is equal to y. Verifying condition A1. Like I said before, I will skip A2. It's not difficult to see. Then for A3, it's also not difficult. I quickly get this done. It takes x, y, z in capital X. So we compute the infinity of x comma y. This is the maximum between xi minus yi. I less than or equal to 1, greater than 1, but less than n. This is the same as maximum between absolute value of xi minus any other point zi, and then this. Okay? I'm sure this is not difficult to see. We've done this many times, so it's clear. And then we apply absolute value property, which is the triangle inequality. So this will give us less than or equal to maximum between the absolute value xi minus zi plus zi minus yi in absolute value. 1 less than or equal to I less than or equal to n. From here we get that this is the max xi minus zi plus the max zi minus yi. 1 less than or equal to I, less than or equal to n, 1 less than or equal to I, less than or equal to n. The infinity of x, comma y is less than or equal to the infinity of x, comma z plus the infinity of z, comma y. And so the triangle inequality is satisfied. Conclusion. The infinity is a metric on x. That says that x together with the infinity is a metric space. That's the verification.